Okay, so again, I'm gonna repeat that we are talking about the anti-Marconicolls addition of HBr to the double bond alkene. No? Again, we're talking about the anti-Marconicolls addition of our HBr, your hydrogen bromide, to your alkene in the presence of peroxide. So the mechanism behind, again, always the first step is the initiation step where there is that homolytic bond cleavage of our peroxide. So nakay OO, nagtapad na sila, no, you get your alkoxy radical. So one of the electrons on the oxygen is unpaired, that's your radical. Once you get your radical, you form another radical, your halogen radical, no? Asa na siya manguha from the HBr, from your hydrogen bromide. Okay, and you will form your alcohol here and a halogen dot or a halogen radical, particular the bromine radical. Once you have your bromine radical, it forms a bond with the carbon containing the double bond. No, it forms a homolytic bond formation, one electron from the pi bond. Okay, you get your Br bond CH carbon here containing the pi electron here, and then one of the carbon will have the unpaired electron. Okay, ang isa gigamit naman to form a bond here. Okay, so you have your radical here. This is a 2-degree radical. And once you have your radical, it can again abstract another electron from your hydrogen bromide. Okay, so you have your hydrogen bromide forming here, forming a bond here. So you have your kani, and this is already like a termination step for this kanilang, for this radical here, kaning alkyl radical here. And then of course you have your Br dot. You can finally terminate this Br dot or halogen dot with another Br dot, no? Or you can terminate this with another this one radical. Okay, mostly kaniyang encounter you have the Br dot for the last termination step. Okay, so in the end, what you can see here is that when it do substitution, no reaction, so what happens? You see here that this carbon here is the carbon containing a higher number of hydrogen, and this one contains a fewer number of hydrogen. Supposedly, this carbon here is where the hydrogen should be added, and this carbon here where should the bromine be added? But apparently, as you can see in this mechanism, no, in the presence of a peroxide, the the hydrogen from HBr is added katong carbon, kaning carbon containing a fewer number of hydrogens, diri ni add si hydrogen, and this carbon containing a higher number of hydrogen, this is where the halide or the bromine is being added. Now, and you have your alkyl halide here, or alkyl bromide. So apparently this is what we call as the anti-Marconicolls addition. And this one is true only for when you are dealing with hydrogen bromide in the presence of peroxide, and we have the anti-Marconicolls addition. So let's have the summary of the Marconicolls results versus Marconicolls reaction versus the anti-Marconicolls addition of HBr to alkenes. In the absence of peroxides, the reagent attacks the double bond first to the proton. Remember your addition reaction in the presence, usually you have your catalyst here as you form a carbocation, you have your hydrogen halide here, no? You will add and you will actually form a carbocation in the process, and you have the Marconicolls product where this carbon again has the hydrogen, and the second carbon containing fewer number of hydrogen contains the halide. So this one, the rich gets richer. This carbon contains a higher number of hydrogen, it gets the hydrogen, and the carbon contains fewer number of hydrogen. We'll have the halide. So this is the Marconicolls product. In the presence of an peroxide, the other way around, it's the other way around. The carbon here containing higher number of hydrogen will have the bromine added, kani, and the carbon containing fewer number will have the hydrogen added. This is your anti-Marconicolls product. Okay, so now we'll proceed on another kind of reaction for your alkenes, and that kind of radical reaction is what we call as radical polymerization reaction. So we again have to consider with a radical, no, by the way, whenever you have that whenever you have your peroxides, always follows or proceeds via the radical polymerization reaction. Radical reactions. So for this section, we'll be talking on the radical polymerization of alkenes. No? So what is that polymerization reactions? So first talk about polymers. Polymers, from polymerization, polymers are substances that consist of very large molecules called macromolecules and made up of repeating units. So it comes from the word poly, which means many, and mers, which means monomers, small part. Okay, so the molecular subunits that are used to synthesize polymers are called monomers. Okay, so many, poly means many, monomers. And the reactions by which monomers are joined together are polymerization reactions. So we have here a repeating substance, molecular subunits we called monomers, and we just repeat that monomers. Usually the monomers here are alkenes. And we repeat that alkenes to proceed with the radical reactions, and then we get poly, too many monomers, too many subunits or basic units to produce a large molecule we call polymers that proceeds via the polymerization reactions. And this usual polymerization reactions actually proceeds with radical reactions. When you say radicals, of course, in the mechanism, before we form the product, it follows the pathways of forming radicals. Okay, unlike what you have learned with addition reaction, because the addition reaction following the Marconicolls, you have in the mechanism a carbocation. In the presence of peroxides, now we actually proceed with radicals in the intermediate step. So it also goes the same here with radical polymerization. Let's look at the examples of how radical polymerization proceeds. So one of the common example or the simple reaction is the preparation of polyethylene. So the poly comes from the monomeric units, monomers, called ethylene. It's an ethylene, of course, it's just ethene, no? The common name for ethene is ethylene. So ethene is like CH2 double bond CH2. So many of this proceeds, many units of this, our monomers will proceed with polymerization reaction. You have your CH2 and another CH2 bonded to each other. Many of that, too many numbers of that, N, sub N. Then we get our polymer. So because there's too many ethylene, we have the polyethylene. So ethylene has been produced commercially since 1943. It is used in manufacturing flexible bottles, film sheets, and insulation for electric walls. Of course, you have already encountered polyethylene. So most of the products, plastics that we are using right now are actually made up of polyethylene. And you've noticed here in the reaction is that we started with a double bond, and as we proceed with the radical polymerization reactions, we actually were able to eliminate with the double bond here. In the same way that you have experienced or have seen in the example of the reactions, once you do the radical reactions, na mawala po ang double bond because we are using the pi bonds from the double bond to form bonds here. So, yun sa man. So, we'll look at the mechanism later. So first, your polyethylenes are prepared by addition reactions, and they are often called the chain growth polymers or addition polymers. So ethylene polymerases, or it's being prepared again by radical mechanism. How? Usually when it is heated at a pressure of 180 amps, or imagine the pressure, it's very, very high, with only a small amount of an organic peroxide. So always you have a peroxide as our initiating initiating reagent, and at a very high pressure. So only small amount of our initiating reactant. So usually our initiating reactant with polymerization of our ethylene is the diacyl peroxide. So what is the diacyl peroxide? Diacyl is when you have your acetyl bond O. This is your acyl group here. And another acyl group, so that's diacyl, but you have your peroxide, oxygen and oxygen bonded to each other always, you get your peroxide, okay? So this becomes our initiator. Once we break this one, once we have this in solution, can easily do homolytic bond cleavage. This one is very unstable in such a way that always produce our radicals here. So you have your acyl radical here, C double bond O, O dot radical. So the oxygen here, one of the oxygen, of course, here there's a double bond. There is a contributing resonance structure here where the radical comes from this oxygen or the radical comes from this another oxygen. So you just do resonance structure, can form a bond here, one electron from here and one electron from here, you get the double bond, and this oxygen becomes would have the dot. So this has a resonance structure. Anyway, this is your acyl peroxide. Again, one of the oxygen contains a dot, an odd electron that comes your radical. And further dissociation of this C double bond O, okay, you actually release your carbon dioxide by again here homolytic bond formation. So one radical here, you get your one electron from the R carbon or another carbon here to produce your carbon dioxide. Okay, 2 moles of that, you get 2 moles of yours. So since you have 2 moles of this, no, so you get your CO2 and then you get your R. But since you have 2 moles of this, and you get your 2 moles of your alkyl radical R dot. So once you get your R dot, you can actually have your chain propagation. This becomes your chain propagation. You get your R from your diacyl peroxide, and you will form again the homolytic bond cleavage. You have this to this. You will have your R bond CH2. So mawala na ang double bond. Okay, nga mawala ang double bond because now we will be using a homolytic bond formation, a bond between this radical here and carbon here using the electrons from the pi bond. Okay, so gamito na itong isa ka electron, gikan ani nga bond, o kani nga carbon here from your alkyl group to produce your R dot or R dash CH2 dash CH2, and one of the electrons from the pi bond will go to this carbon. So you have your carbon dot. So once you have your carbon dot, this another radical, you can do the chain propagation. No, so chain propagation, let's repeat this one with this, another alkene. Okay, so you use again, form a bond with this alkene by homolytic bond formation. So you form a bond between this carbon using one electron from this pi bond. Okay, so kay gamiton na nato na siya to form a bond. Kanina po nga carbon will get the one electron coming from the pi bond. So ang pi electrons will be used to form that here and a bond here. So you have your CH2, of course you have your R, CH2, CH2, okay, and a bond with this, okay, CH2. So daghan ani, you actually produce, just have to repeat the process and repeat the process over and over, and you get actually CH2, CH2, parenthesis, and you have a large units of this ethylene, okay, until you get the termination step, where we encounter another radical here for the step to be terminated. But unless this radical encounters another alkene, then the reaction will proceed, and the chain length will now depend on how long will you proceed the reaction or the condition. Okay, and yes, this one is a combination. Another one here, you have large step kani chain propagation. As I've mentioned, you can have your termination with another radical like this one to produce this. So my end siya no times 2. Or you can have the disproportionation reaction. How is the disproportionation reaction? Okay, radical here, you just get another electron from the hydrogen, okay, it's Cleavage, and you will actually have your double bond again. Okay, and then you will have your dot, or this one to be abstracted kani katong, of course you have your, you get your hydrogen here. Okay, your hydrogen kani, should I show you? I think you can follow that now. So you have your CH2. Okay, you will get, you form a bond with the hydrogen here by homolytic bond cleavage. Okay, so you will have your CH now, CH2, and then another mole of that H dot, no? So you have your H dot. Okay, may eliminate man si isa ka hydrogen here. Okay, and then another H dot will be formed in ani. And this is the termination products here. Okay, so alternately, you can also have chain branching. How is the chain branching occurs? The chain branching is once you have the radical here. No, you have your radical here. Pwede nyo i-abstract ang hydrogen like few carbons away, like a very few carbons away, to have that, to have this kanina end that to be terminated, and kanina siya nga carbon like few carbons away to have the radical. So once you have the radical here, diri na din siya mo proceed with reactions sa double bond, like CH2, double bond CH2, and that's where you have your carbon, and another CH2, and this is where the dot is. Again, how is it being connected? Electron of another electron diri sa double bond, no? That is how you form a bond here. And since gigamitan nato og electrons here, okay, hello again. So there you go for the branching step of our alkenes. Alkenes, our ethene rather, no, having our polyethylene. So when we prepare polyethylene, there's actually that linear polyethylene, kanang not branch, straight lang gid iyang formation. There's also that kind of polyethylene that is branch. It's a branch, kanang straight na siya, and then there's somewhere here in the chain length that is, there's the alkane branching here. Okay, so again, when we prepare our polyethylene or polymers now called polyethylene, it proceeds via the radical reactions. Do you have questions? Asa man ang uban? Di ay, ano man ang uban? So the polyethylene produced by radical polymerization is not generally useful unless it has a molecular weight nearly 1 m. Very high molecular weight of polyethylene can be obtained by using low concentration of the initiator. Okay, It depends on the molecular weight that depends on how much we're using, how much initiator are we using. And if you use a very few concentration of the initiator, you get a low molecular weight polyethylene, and this initiates the growth of only a few chains and ensures that each chain will have a large excess of the monomer available. So daghan tag excess ng monomer for this, okay? Gamay raman natin initiator. But if you use more initiator, as the chains terminate during the polymerization, new chains began. So that's why you have a very high molecular weight when you have high chain. So there's this called polyethylene can also be prepared in different ways using the catalyst, Ziegler-Natta catalysts that are organometallic complexes of transition metal. So what is that? You can watch on the video. This one is prepared via the use of a Ziegler catalyst. By the way, there's two kinds of polyethylene, the low density polyethylene and the high density polyethylene. So the high density polyethylene, you have your HDPE, and the low density polyethylene, low density means you have the LDPE. So later we'll look at on the difference between the HDPE and the LDPE in terms of its structure, and we can even now think which one would be highly branched structure, or which one would be more will have the structure in a linear lang polyethylene. Okay, so again, you have here the conditions with the LDPE usually have at a very high temperature, or higher temperature than the normal temp. You have 200 degrees Celsius is a very high pressure. With HDPE, we actually prepare this one using the Ziegler-Natta catalyst. And what's the Ziegler-Natta catalyst? This one, the titanium trichloride, titanium chloride, and aluminum diethyl chloride here, and at a very low temperature and low pressure. By the way, madunggan ninyo ang kuan. Dunggan ninyo ang video.
Dili, ma'am.
Ha?
Dili madunggan, ma'am.
somewhere above 400 degrees C.
What
Now,
about
in this
now?
structure, each titanium, as well as being bonded to
Maklaro
3
ninyo?
chlorines,
Maklaro na ang sounds.
because they have
Anyway, you
got
can
3
watch the
empty d
video later.
orbitals, 3 dative covalent bonds will form from pairs of electrons from chlorines on adjacent molecules. Now, around each titanium then we have 6 bonds, 3 covalent and 3 coordinate bonds. Now you'll see that I'm cheating a little bit here. It's difficult to present this three-dimensional structure. You'll see a pattern will bond, and this
Okay.
process.
So since di mo ka paminaw, no, di niyo madunggan, just watch the video later when you have time. So we'll proceed with the reactions, the polymer reactions. Anyway, what we have learned so far, and what we have learned is that with polyethylene, there is two kinds of polyethylene, no? The high density polyethylene and the low density polyethylene. No? So the high density polyethylene actually have a more linear structure. No, it's not branch. And because it's not branch, no, imagine you have a linear structure. Imagine when you have a linear structure, no, like this one. For a for HDPE. Or high density polyethylene. So the polyethylene that you actually produce here are of linear structure. It's not highly branched. So in such a way that you will find that there is a strong van der Waals force of interaction between the linear chains. And because of that, you actually have a strong interaction between the chains. And you expect that this one would have a higher melting point and a very high strong interactions between the linear chains. The other one is the low density polyethylene. No? In the low density polyethylene, you have branching in between the structures. Okay, so if you have, for example, chains of your low density polyethylene. No, so what happens is that with the linear structure, ng lagyo siya, and because of that, the volume is very the mass is very low, but the volume is very large because this one is more disordered and disorganized in the low density polyethylene. So the interaction between them actually between the chains is actually weaker than the one that we see with the high density polyethylene. In fact, this one with the HDPE, we can see that it's more in a crystalline structure as compared to the LDPE here. And of course, the mechanism for which we prepare our HDPE and LDPE are the conditions for which we prepare those two kinds of polyethylenes are different. And we have already mentioned that in the video. So now let's proceed with another kind of polymer. Another kind of polymer. So before we end today, we have to finish polymers so we can start chapter 11 next meeting. So another kind of polymer is the styrene. Okay, the styrene or polystyrene rather. The polystyrene is prepared from the styrene. You have your benzene ring with a double bond here. So where would the radical reaction goes? So this is where the radical reaction goes here. This one will be forming a bond with another alkene here. And so this is, you have your alkene. You have your alkene and forming here, and another alkene you have here. Another alkene, alkene, alkene. You have here alkene added here. You have alkene. Mawala si double bond not to form a bond here. You have here. So this is where you have your polystyrene you can see that the double bond is lost because this one is used, the pi bond is used to form a bond with the other styrene molecule, no, using a homolytic bond formation. So you have different kinds of monomers actually, no, and you produce different kinds of polymers. For example, you have your propylene, you have 1, 2, 3. You have your propylene, no. So this will become your repeating units. This you have your carbon 1, 2, 3. Okay, this is where becomes your repeating unit. You have your vinyl chloride, 2 carbons and chloride. You have your vinyl chloride, it becomes your polymer will be your polyvinyl chloride. And this is again your monomer, and this is your repeating unit. You have your acrylonitrile. You have acrylo and you have your nitrile here. And so you have your polyacrylonitrile. And then you have your tetrafluoroethene, ethene with 4 chlorine. You have your tetrafluoroethene, and repeated one, you have your poly tetrafluoroethene here, or PTFE. The other name for this is PTFE or Teflon. Okay, or LON, PVC, polypropylene. Another one is you have your methacrylate, methyl. This one is 1, 2, 3, 4. Branched here, methacrylate. Methacrylate, you have zero bond O here. So this is just a common name. No? Polymethacrylate, you can have this one common products. You have the lucite, plexiglass, and perspex. Perspex ka na bitang mga, you can see the plexiglass no, nga mura siya o glass. Transparent siya, but it's not made up of glass, but it's made up of plastic. Kanan sa mga swimming pools, no? Kanan swimming pools nga clear, or sa mga aquariums nga dagko, no? It cannot be glass, no? Because the glass is made up of silica and it couldn't withstand a very, very high pressure. But this, with this kind of polymer, it can actually withstand very, very high pressure, no? Kanan sa mga dagko na bitong aquariums, no? Kana makabantay mo ng underground kanang kuan, underground aquarium, right? Or you have a swimming pool that's clear. It's made up of polymethyl methacrylate. So you have the plexiglass, or if you have, for example, plastics at home, no nga mura siya glass pero dili di ay, okay, that's made up also with this polymer. Teflon, kanang pang Teflon, kailangan siguro mag Teflon na pang bind no sa mga PVC, sa mga edgings niya. Okay. Of course, you have already encountered PVC and polyethylene. Polyacrylonitrile can also have here from the carpets, kaya mga uban nga fabrics, no, carpets. Okay, so another one. Can you suggest an explanation that accounts for the fact that the radical polymerization of styrene to produce occurs in a head-to-tail fashion? Head to tail. Okay, you'll notice here you have your polystyrene. This is your styrene here. Your head to tail, no? So you notice here you have your phenyl ring here, and you have your CH2 double bond CH2 here, and then this is, for example, our head, and becomes our tail. So here you have your forming a bond here, kaning obos, becomes a head forming here, and becomes our tail here. So you have kani. So when we add electrons, form a bond, we use the electrons coming from this carbon here, form a bond, kani. This becomes the new bond. And what we have is kani, this becomes the radical. So put another, this one, it will add, this one again will add here, and then you form another one here, and then put another you have here. So can you suggest an explanation that accounts for the fact that the radical polymerization of styrene? So do you have an explanation for this? Can you suggest an explanation though? Why would that be? So the question of nganong head to tail, nganong diri man, diri, not here. Okay. Can you suggest an explanation that accounts for the fact that the radical polymerization of styrene to produce polystyrene occurs in a head to tail fashion. So it becomes head and tail. So kana, and then this becomes your radical. You get another of this, no? Tanaw ninyo na. So sumpayan nato niya. You have here another of this. Okay, you will have here one electron coming from here and one electron coming from there. And so we copy this one. You have your R, okay, C6H5. What is that C6H5? C6H5 is just this. This one. Kani. This is the 1 to 6, and you have 5, so that is your C6H5. This is your phenyl. Phenyl, it's a ring, no? Without the part. Without one siya labot, you have 6. It's your C6H5. Okay. And then of course you have here, copy that. You have your C6H5. C6H5. Okay, and then you have form another one. Isa na to ni siya blue. This becomes your new bond. And then you have your red. Continue with the red. You will have your kani. Okay, you have your red. One electron would go there. Okay, one electron will be used to form a bond. One electron from the electron here, from the radical here, and one electron from the carbon here. Kani mong form the blue, and then you will have your electron that diri, so you have your kana, and then so that's carbon 1 kani and carbon 2, and then you have this C6H5, and this becomes your dot. Okay, so you've noticed here, instead of inani, no, that head to head, if this is the head, kani, you add here. Why is it that you have always the head to tail and not head to head? Kaning head to head, you have kaning a part, kaning a head. Okay, see, kaning mong electron, this becomes here, and so copy that. You again have dili pud siya mo add na part, and you always produce your radical here. Again, the reason behind na dili mong radical, terminal siya. Of course, the reason behind is here you always get your 2-degree radical. Okay, and this one you always get your 1-degree radical. And of course, we've learned that between a 1-degree and a 2-degree radical, the 2-degree radical is much more stable than the 1-degree radical. And that's the reason why when the polystyrene is being prepared, no, it prefers to have the head to tail manner of producing its